Okay, this is from week 6 on Wednesday, 2014. This is slide number 20, the question from that. You observe a double-line spectroscopic binary. The orbital period is p equals 8.6 years, and the maximum Doppler shift of the Balmer series first transition, which is normally centered around 6,562 angstroms. The shift for star A is 0.068 angstroms, and the shift in the wavelength for B is equal to 0.72 angstroms. The radial velocity curve is nearly sinusoidal. This is our hint that we can get rid of our sine I term. The light curve indicates that it is an eclipsing binary. And so an eclipsing binary, when you have a star and the other star goes around it and it's going around in a circle, that means that your line of sight, as you're looking at it, you're going to get your maximum Doppler shift. So as one star is rotating around the other one, the light is going to be, the light that you see will be completely redshifted or blue shifted in accordance with the velocity, as opposed if the system were two stars revolving around this way and our line of sight is on this axis, we would only, this vector here, all we would see is the corresponding vector, and it's called I. Anyways, forgetting about all that I crap, let's pull out our formula. I believe we haven't used this one before. This is very similar to what we've been doing in class. And I haven't derived this. This is a gravitational constant, not a 6. And this is normally VAR plus VBR to the third power. So you can see this looks very similar to what's his name? I can't remember his name right now, but anyways, the information that we have that the radial velocity curve is nearly sinusoidal and it's an eclipsing binary tells us that our angle here, I, so angle I is it this angle? It has to be sine of pi over 2. So yeah, it's this angle, because if it has to be pi over 2. Anyways, the point is this goes to 1, so we're just left with mass of star A plus the mass of star B is equal to the period, which the period is in years. We have to have it in seconds. And period over 2 pi g and the gravitational constant, that is going to be equal to 6.47 times 10 to the 17th. So that's an easy calculation. Put this into seconds. Use your regular gravitational constant. That gives you this wonderful number right here. Now this right here, we don't have any velocities. We have change in our wavelength. Well, how are we going to get this? If we're normally wanting some kind of velocity term here, let's look at velocity of A right here. Well, that's usually in meters per second. Well, we do have something that's in meters. We have this change in alpha A, or change in lambda A. So we could construct something with lambda A here, and that was the change in lambda A, but what are we going to use for the seconds? We can't use this, we're already using it over here. let's see, what if we... period is measured in seconds. I'm not going to put period there, but let's look at the period, which is measured in seconds. The period is measured in seconds. Well, what is 1 over the period? That's the frequency. And what is the frequency? Frequency is the speed of light over your wavelength. So, working this backwards, if you want your period here, and your period is equal to 1 over your frequency, and your frequency is equal to c over lambda, then you have your period is equal to lambda over your speed of light. And using speed of light for the velocity term is very appropriate for light being traveling in space. Okay, and since this is on the bottom, we will have our lambda. This is kind of lambda naught, and times the speed of light. So this is what we need to plug in to here and do the same thing for this one in order to calculate this. Let me get some more room over here. So the mass of star A plus the mass of star B equals to 6.47 times 10 to the 17th times. I'm certainly going to need some more room here. Times. Let me just erase this real fast. So, does anybody ever watch these stupid videos? So just my own personal study aid. I would love to hear from you if you actually listen to this diatribe. Okay, so we have lambda, or change in lambda, over lambda times the speed of light, plus, we got for star A, change in lambda for star B times the speed of light, over our lambda, all of this cubed, that is ugly looking 3. Okay, this is going to work out to be, I already did all the calculations for you, aren't I wonderful? This works out to be 3.025 times 10 to the 31st, obviously, kilograms, dealing with mass. And this is a really big number. Let's put this in terms of the sun. Okay, we know that the mass of the sun has this many kilograms, roughly 2.0 times 10 to the 30th. That gives us a mass A plus a mass B is equal to about 15.13 solar masses. Okay, so how do we figure out which one, how much of what is what here? What's going on? Just like the visual spectroscopic binary star systems, which has a relationship of like the mass of one star to the mass of the other was equal to, let's see, what was it for them? It was the semi-major axis of A, the semi-major axis of this revolution to the semi-major axis of star B. The exact same comparison with our wavelengths. We can have our wavelength A over our change in wavelength of A over change in wavelength of B, and our change in our wavelength at A was what? Actually, I want to do this backwards. I want to do A over B. So I just switch these. I want mass of A is a ratio to the mass of B. That gives me the lambda of my star B to my lambda of my star A. And you'll see why in just 1 second. So changing lambda of B was 0.72. And that's angstroms, but since it's a ratio, it's going to cancel out. Lambda, the change in wavelength for star A was 0.068, and that equals a nice little number, 10.6. And that's why I wanted the larger one on top, so we could get a bigger number, not some fraction. So I can relate this to my masses, which would be my mass of A related to my mass of B, is equal to 10.6. It's just an inverse relation here. So that gives me the mass of star A is going to be 10.6 times larger than the mass of star B. Using this information, I can replace my mass here with this and add 1 to it. 10.6 of the mass of star B plus 1 mass of star B equals to 15.13 solar masses. This gives you 11.6 mass of star B. 15.13 solar masses. Divide, you're going to get your mass of star B is equal to 1.3 solar masses. And just using the fact that MA plus this amount equals 15.3, I can take 15.3, subtract this amount to get my mass of star A. And that is going to be, I calculated 13.83 solar masses. On the slide, he lists 14 solar masses, which is pretty darn close. And see you next time.